I have no plans.
The notes that we are taking are on Eulers Method. And this does not look like it's pronounced Euler, but it's a dude's last name. Euler. Euler. Eulers Method. Not Euler. Nope, not Euler. Euler. All right, so Euler's method is a numerical approach to finding a particular solution of a differential equation. So the slope fields are what we did yesterday. Slope fields were a graphical approach of general solutions, right? You can see all the different solutions, all the different equations on a slope field. So now we're looking at a specific solution for a differential equation, which would be like a specific equation. It uses parts of tangent lines. Hey, you gonna learn with us today?
Yeah.
All right. It uses parts of tangent lines to approximate the solution. So we did something kind of similar to this idea. The math was different, but we did something similar to this before where we couldn't necessarily figure out exactly where the curve was, but we could figure out maybe what the tangent line could be, and we said that that tangent line was a good enough approximation that we could use it as an answer. Do you guys remember doing that? Can't find the curve. We don't know the equation of the exact curve, but if we can find the tangent line, we can get an answer that's reasonable enough that we can go ahead and say that's pretty accurate. So that's basically what we're going to do today. So there's some information that they're going to give you in the problem that you're going to work with. One is the initial point. So that's an x and a y coordinate. So I have x sub 0 and y sub 0. That's like an initial x value, an initial y value. And so if you guys remember how those slope fields work, we have little line segments that go on each point. So we always have to start with a point because we have to know what point we're plugging into that differential equation to find the instantaneous slope of whatever point we're looking at. The other part that we're going to be given is the differential equation itself. So if you guys remember, the differential equation might be written as like y prime equals whatever you get when you plug a point into a function. So they wouldn't actually write it as f of parenthesis x comma y. It would be some sort of function there, and you would get the slope by plugging a point into the function. Okay, so I'm going to say aka m. That's going to be how we find our slope, because a derivative is an instantaneous rate of change or an instantaneous slope. And then the other thing you're going to need is the step size. And that tells you how long your little line segment is. So step size, and they write it sometimes as h, and that h would be kind of related to back when we were finding the area underneath a curve using rectangles, and we had h as being like the height of the rectangle, or dx is like the width of the rectangle. That's what they mean there. Or they call it delta x. Do you guys remember what delta x means from back in the day? Change in x. Yep, it means change in x. So that's the information that you're going to be given. Okay, so when we look at these, when we look at Euler's method, it's going to give us a recursive function. Do you guys remember what recursive means if you were studying like arithmetic and geometric sequences? Do you guys remember that? There was explicit and there was recursive. Does that ring a bell?
It rings a bell.
It rings a bell. Recursive is the one where you say, based on the number I just had, I just continue this pattern. So the recursive formula might be take the number before it, multiply by 2. Take the number before it and add 2. So everything in a recursive pattern is saying, based off the number you just got, now we can get another number. So if I ask you to use Euler's method to find the 17th term of something, you're going to have to find all 17. You can't just go straight to the 17th. You have to find all the ones before that. So that's the part of today's assignment that's going to be kind of tedious, is you have to do all the math to lead up to it. Now, I'm not going to ask you to do the 17th, but when I ask you to do the 4th, it's going to be annoying because you're going to have to do like a tedious amount of work to get there. It's not necessarily hard, it's just tedious. All right. So it's a recursive function. So I'm going to describe to you how we find the x-coordinates and how we find the y-coordinates of this recursive function. So I'm going to go ahead and make a table. And I would not put the table up next to the margin of your paper because we're going to have to write a few things over here. So we've got our x-coordinate and our y-coordinate. We always start off in our table with that initial value. So x sub 0 and y sub 0. That's our initial point. And then we would say that the first x-coordinate would just be the initial value plus that change in x or whatever that distance is. So you can put plus h, you can put plus change in x, it doesn't matter to me. All right. The next x value would be if we took the first one and added that same change. The third term would be if we took the second term and added that same change. So do you guys see how we're getting those x values? So if we're going to say that it increases by 2 every time, then just take the previous number, add 2. Take the previous number, add 2. Take the previous number, add 2. And you can get all the rest of them. Okay. So if we were to generalize this to like a formula, we would say that the nth term would be what? Yeah, x sub n minus 1 plus h. So the x's are easy to figure out because they are the independent variable, right? You choose what you want the x to be and then you plug it in. That's how you find the y-coordinate, right? Okay. So those are pretty easy. When we write this down to make it make a little bit more sense in our heads, we're going to think of this as our new x value is just going to be our old x value plus the change in x. So our new x value is just the old x value plus the change in x. So x sub new equals x sub old plus delta x. Okay. Now, these are little line segments that we're coming up with, right? That's what we looked at with the slope field, is we have all these little line segments. So what's the equation of a straight line? Y equals mx plus b, right? Okay, y equals mx plus b, that's the equation of a line. And that actually helps us come up with our next y term. So the first y term is going to be the slope. How do we find the slope? You plug in the point. Okay, so what we're going to do is we're going to say if I take the function and plug in the point that I have from up here, so that's me plugging in the point, then I'm going to multiply it by my x-coordinate. And my x-coordinate is going to be that width. We're going to use that width of x, so we're going to say that this is going to be multiplied by h. So the slope multiplied by that width plus the initial value, which was y0. Now this one follows a pattern too, so we're going to say our second point, or our second y-coordinate, is going to be the function if you plug the first point into it and multiply it by that same width, and then add the y-coordinate. And then the third point, or the third y-coordinate, would be calculated using the same method. So this is the tedious part. You guys seeing it? The tedious. All right. So if we jump down here and say now we want to write the nth y-coordinate, what would we have? We're plugging a point into the function. What are we plugging into the function? N minus 1 and y sub n minus 1 times h plus y sub n minus 1. So that notation is kind of confusing, right? A little bit confusing. So we're just going to say that our new y-coordinate is the slope times the change in x plus the old y-coordinate. So the new y-coordinate is the slope times the change in x plus the old y-coordinate. Whew. Okay, how are your brains feeling? Thank goodness we're going to be out of class soon. Is that where we're at? Okay. So go ahead and write this part down. Yeah. We're gonna describe it a little bit more, and then we're gonna do it. As soon as we start doing it, you're gonna be like, yeah, I can see how that's annoying, but capable. You'll be capable of doing it. Okay. So we're gonna say the smaller the step size, the better the approximation. And that's because smaller line segments make a smoother curve. So the smaller the step size, the better the approximation. And that's because smaller line segments make a smoother curve. It's going to be closer to the actual solution if we have smaller line segments. Now the reason we would not do infinitely many is, again, this is a super tedious process. So this is kind of like when we were doing integration and we were finding the area underneath the curve. Our integration or our area would have been more accurate if we used 100 trapezoids every single time, but doing 100 trapezoids every single time would have been a pain in the butt, right? So we maybe just did 5 because that was reasonable enough for us, and we said, okay, we'll call that good. It was tedious, but not overly tedious. Same thing here. If we did 100, that'd be better, but that would be super tedious and terrible, so let's just do 5 and call it good. Does that make sense? Can we do it that way? So if you draw, let's go ahead and draw a picture of a curve. This is just like some exponential graph, and I want to show you guys what the difference in the steps would do. So you're going to draw the same curve twice. And on this one, we're going to do it in 2 steps. And on this one, we're going to do it in 4. So same distance, just the step is going to be different widths. So if we were to come up with line segments that went with the first one, we would say that right here, if this is our first x value, the line segment that would represent that slope right there at that point would be slanted kind of like that, a pretty flat slant. And then if I think about this x value right there, the line segment that would fit that would maybe look like this-ish. So if I do 2 steps, that's like reasonably close to the curve. Probably not the best you can get. Does that make sense, how it doesn't curve quite the same? Okay. If we look at this one over here, there's my first step. There's my second step. What do you guys notice as we do this one? Yeah, the more steps you have, so the smaller your change in x, the better your approximation of the curve is going to be, the closer you're going to get. So we might not know the actual equation of the solution to that differential equation, but our tangent lines will be close enough that we can say we essentially have it, we have mathematical answers that are reasonable enough, we are comfortable using them. Okay. So here is how we're actually going to do it. The problem might say to use Euler's method to approximate the solution for the differential equation y prime equals x minus y through 0, 1 with a step of 0.1 and 4 steps. Okay, and to do these, we're going to fill out a chart because we have lots of numbers to keep track of. We have old y-coordinates and new y-coordinates, old x-coordinates and new x-coordinates. We have the delta x that we have to keep track of, and then we have the slope that we have to keep track of every time because each of those little line segments has a different slope, a different y-intercept, a different x value, a different y value. Does that make sense? So we're going to do this in a chart so we can organize our information. So I always start off the chart doing the x and y coordinate that we're starting with. So I'm going to say my old x coordinate and my old y coordinate. And it says that the starting points we're going to use are 0 and 1. And they ask us to do a step of 0.1 and to do it 4 times. So that step of 0.1 is the change in the x value. So I know after the first step, my x value is going to be 0.1. After the second step, it's going to be 0.2. Then it's going to be 0.3. Then it's going to be 0.4. So that's how big my chart needs to be. I'm going to keep track of delta x, although I know it's going to be the same every time. My change in x is 0.1 every time. I'm going to keep track of the math that I do to find my slope. And if you guys remember, the slope comes from the derivative. So I'm going to need that derivative equation so I can calculate my slope. Because this involves some math and because these numbers often become decimals, you want to leave yourself enough space that you can actually write down some numbers in there. So don't make that column too skinny. And then the next part is where we're going to figure out the value of our new y-coordinate, because the value of a function is the value of the y-coordinate at whatever you plug in for the x value. So if you say, I want to know what the value of the function is at 5, then plug in 5, it'll tell you the value of the function. So if they're asking you ever in a problem the value of the function, they really want the y-coordinate. And if you remember, the way that we defined how we could find our new y-coordinate is we would basically do y equals mx plus b. So that's the next part in our chart, is we're going to say we're going to do our slope times our change in x plus the old y-coordinate. And once we do all that math, that's going to give us the new y-coordinate. So when you do these problems, you're going to set it up the same every time. You're always going to make this chart. And now you need your calculator. Woo-hoo. Okay. So first column says the slope is based off x minus y, so 0 minus 1. So what is our slope for the first one? -1. So we have -1 times the change in x plus the old y-coordinate, which is 1. So my new y-coordinate is -1 times 0.1 plus 1. So my new y-coordinate is 0.9. Can you see how I did that? So I found my slope first, x minus y, and then I plugged in my slope, and I plugged in my change in x, and I plugged in my old y-coordinate, and I got my new y-coordinate. So this new y-coordinate drops down. So one of the points that I would expect to find on my specific solution to the differential equation would be the point 0.1, 0.9, x-coordinate, y-coordinate. I would expect to see that. All right, and then we do it again. So we've got 0.1 minus 0.9. It is tedious, yep. Is -0.8 times 0.1 plus the old y-coordinate. And what are you guys getting for your new y-coordinate? 0.82. So another point that we're expecting to see would be the point with an x-coordinate of 0.2 and a y-coordinate of 0.82. And then we do it again. So we've got x minus y. Are you guys seeing why we get satisfied with like 5 steps of this and not 100? Yep. Yeah, these are not my favorite. All right, so then we've got x minus y again. And at this point, we don't have to finish the chart because all they wanted was the solution after 4 steps, and this is the solution after 4 steps. So the value of the function after 4 steps would be 0.712, because that's the y-coordinate. So the function has a value of 0.712 after 4 steps if the steps are 0.1 width. All right. How are your brains with that? Tedious, annoying? Yeah. And we're going to say approximately. Why are we saying approximately? Yeah. What's the only way to get an actual answer? Not a fraction, but think about what we're doing here. Do we have the actual solution to the differential equation? No. So the only way to get an exact answer here would be if you knew the exact solution to the differential equation and you were plugging 0.4 into that. But we don't know what the actual solution is, and so we're just approximating it where we think it would be. Okay? Does that make sense? Yes. Okay. All right, we're going to try another one. This one is going to be, we're using Eulers Method again. We're going to say y of 1.6 when your differential equation is y prime equals x divided by y through the point 1, 1 and h equals 0.2. So this problem is identical. It's just that they are giving you the information phrased a little bit differently. So I'm going to start off my chart the same way. I've got x old and y old. Does anyone know what my next x value would be? 1.2, yep. And then how far do we need to go with those x's? Can you tell? The notation is kind of weird. To 1.6, yeah, this is saying find the y-coordinate when the x-coordinate is 1.6. So it's like function notation, but instead of saying f of x, they're writing it like y of x, plug in this x value to find the y value. So if we're going by 0.2, we have to do 1.2, 1.4, 1.6, and when we get that y-coordinate that goes with the 1.6, we'll be done. So I know that my delta x is going to be 0.2 every time. I'm going to figure out what my slope is by using this differential equation. So taking the x-coordinate and dividing it by the y-coordinate. That's how I'm going to find my slope. So that column can be pretty narrow this time because that's not hard to do, to divide those two numbers. And then I'm going to have slope times the change in x plus the old value. That's going to give me the new value. So for the first one, the slope would be x divided by y, so that's 1 divided by 1. So that gives us 1 times 0.2 plus 1. So our new y-coordinate is 1.2. And then we'll do the same thing again. So the slope is going to be x divided by y, so 1.2 divided by 1.2. Again, that just equals 1. So plus the old y-coordinate, so we've got 0.2 plus 1.2 is 1.4. So the new y-coordinate is 1.4. If we do x divided by y, and that gives us 1 times 0.2 plus 1.4 is 1.6. And so all we had to figure out was the value that you get for the y-coordinate when you plug in an x-coordinate of 1.6. So I'm going to say that when I plug in an x value of 1.6, I get approximately 1.6 as the value of that function.